I just got back from Switzerland where I visited the most insane place on Earth, CERN. Hidden beneath Geneva, Switzerland, there is a 27-kilometer long tunnel buried 100 meters underground that is colder and emptier than outer space. Inside it, particles are accelerated to nearly the speed of light, circling the loop 11,000 times per second before they are smashed together at temperatures 100,000 times hotter than the sun's core. These collisions recreate the exact conditions from the very birth of our universe, the Big Bang. CERN is probably the only place in the entire universe where such insane science happens, and by the end of this video, you're gonna understand exactly how it all works.
The Large Hadron Collider.
The God particle. Mini versions of the Big Bang.
Oh my god. I was so excited for this trip because honestly, CERN has been the one experiment on Earth that I've been obsessed with since I was a child. They are basically using these massive particle smashers as the world's most advanced microscopes to try and figure out what actually makes up you and me. But for us to understand how they actually do all of that insane science, we need to head down into the tunnels. To get down into the tunnels, we had to pass through a number of security checks that made me feel like James Bond. I even had to do a retina eye scan to get clearance. We entered the elevator and descended over 100 meters into the Earth, where the LHC lives. And finally, it was time to see it. Oh my god. It is massive. I couldn't actually believe my eyes. It looks so beautiful and crazy on video, but I'm telling you, nothing will compare to actually seeing it with my own eyes. This thing weighs more than the Eiffel Tower, and it is buried deep underground, so we can smash particles together. But my question was, how do they actually smash these tiny little protons into one another?
So the width of the proton beams is about the width of a human hair.
Firing protons one by one at each other would take millions of years to get any meaningful results. So instead, CERN fires packets of more than 100 billion protons at each other. They make two beams, each containing around 3,000 packets, and have them racing in opposite directions. And then they have the beams meet at very specific points, colliding. For every interaction between two packets of 100 billion protons, just 50 actually collide. The rest just simply zip past each other.
So yeah, they cross over each other every 25 nanoseconds.
This means you have over 40 million of these packet crossings every single second. And this is only possible because the particles are traveling at nearly the speed of light. A mind-blowing consequence of Einstein's relativity is that from the proton's perspective, the LHC's ring isn't 27 kilometers long at all. Because the protons are traveling really close to the speed of light, they experience an effect known as length contraction. This causes the entire circular tunnel to appear to be just 3.6 meters long from the proton's perspective. Okay, so trips like this around the world where I get to visit places like CERN would not be possible without our amazing brand partners, which is why I'm so excited to tell you about Revolut, because between you and me, I've been using their services for many years now. Revolut is a financial super app that combines all the aspects of managing money into one simple and easy to use app. And the best part is, you could get $40 when you download Revolut and pay for something using your card. Just click the link at the top of the description or scan this QR code to learn more. Personally, my favorite part is when you sign up to Revolut, you get to design your very own custom card however you want it. And if you sign up with their metal plan, it's a stainless steel card that both looks and feels amazing. The reason I personally signed up years ago was for their currency exchange features. So when I'm traveling places like Europe and the US, I can quickly exchange money without having to think about it. And it gets even better. There are no fees to get money out of ATMs anywhere in the world. You can even use their app to set up an eSIM or get access to discounted lounge passes at the airport. If you were overseas and you lost your card, you could simply just pause it in the app in seconds so you don't have to worry. Like I said, I've been using Revolut for years before they ever decided to reach out and work with me. And here's the best part. When you sign up to Revolut using the link at the top of the description, you'll get $40 transferred right into your account as soon as you make your first purchase. It's that easy.
And right now we're walking under the LHC. So when we're on 6, we'll see where the Large Hadron Collider is. If you were here when the Large Hadron Collider was on, like in this cavern, it would not be good.
Not good for you.
You would not make it.
CERN didn't start with the Large Hadron Collider, that massive 27-kilometer long loop. They started small and had to work up over time. They built the synchrocyclotron in 1957, achieving collision energies of 600 mega electron volts. And then came the proton synchrotron. It achieved 50 times higher energies and would be crucial for developing the field, but the energies were still not high enough to discover something groundbreaking and amazing. Then came along the first collider to smash particles head on. They doubled the energies again, but still no breakthrough. So they went bigger, creating the Super Proton Synchrotron, achieving energies nearly 8 times higher than the last collider, and finally, breakthrough. They discovered the W and Z bosons, which are these kind of fundamental particles that confirmed the weak nuclear force, earning the lead scientists the Nobel Prize in 1984. But one piece of the puzzle was still missing: the Higgs boson, which describes how particles get their mass through the Higgs field. To find it, CERN built the LHC, capable of reaching 14 tera-electron volts, 30 times more powerful than the SPS. That amount of energy squished into a space that small produces temperatures hotter than anywhere else in the universe today, hotter than the hearts of stars or even supernovae explosions. There has only ever been one time in the entire history of the universe where events this energetic have occurred, and that's literally during the Big Bang. And it worked. In 2012, they confirmed the discovery of the Higgs boson, the crowning jewel of CERN. There was one thing that I still didn't fully understand. Once they smash these protons together, how do they actually find these new particles like the Higgs boson? Imagine 2 protons speeding towards each other at essentially the speed of light. If you had a little microscope and looked inside the protons, you would find a couple of quarks that are stuck together by gluons. These are elementary particles, and as far as we know, that is as small as it gets. When these 2 protons collide, they get smashed into pieces, sending elementary particles flying off in all different directions. If we just pause time right after the collision occurs, let's see what we can find. We can see all different kinds of particles that were created in the collision: pions, kaons, mesons, and even photons of light. These are the fundamental building blocks of matter. But what's that? Occasionally in these collisions, you can create extremely rare and heavy particles. This one is the God particle, the Higgs boson. But the thing is, time is paused here, and this little guy will decay away into different particles way faster than we can see with the detectors at CERN. In an instant, the Higgs morphs into multiple smaller particles, and then it's up to the physicists to actually look at these baby particles and turn back the clock, inferring the brief existence of the Higgs boson. And that process is essentially exactly what CERN does with the LHC. They smash the protons together and then use these massive detectors to have a look and see what comes out. And this is how they are recreating the exact conditions of the Big Bang and why it's so insane.
The very early universe was this really hot, dense, we call it a soup sometimes, this quark gluon plasma soup.
This tasty soup is made out of quarks and gluons, the building blocks of the protons and neutrons that make up you and I and everything else in the universe. During the particle collisions, these fundamental particles get superheated, causing their bonds to kind of melt away, creating the quark-gluon plasma. This soup has only ever existed in 2 places in the entire universe. 1/1,000,000th of a second after the Big Bang, and in Geneva at CERN. Okay, so by this point, I feel like I was finally wrapping my head around it. You need a larger collider so you can smash these particles together with more energy, which means you can produce more rare and exotic high energy particles. So I was wondering what would happen if they just went bigger. Would they find particles that are even more rare than the Higgs boson?
We have basically chains of accelerators that use, and they will get bigger in circumstance. And the reason why we do this is because if you have a charged particle and you accelerate it on a circular line, you have an effect that is called synchrotron radiation. So you lose the energy, and this is depending on the radius and the speed you're going. So you need to go bigger in radius in order to lose less of this energy.
There are plans to build a new collider, the Future Circular Collider, capable of achieving energies up to 100 tera-electron volts, nearly 10 times higher than the LHC today. Who knows what insane physics we might find at those energies? If they made this new massive accelerator, they could potentially find new particles beyond the standard model.
The standard model of particle physics is our best recipe book of what the universe is. So a lot of people will be familiar, for example, with the periodic table, and it's one level down. So it's the periodic table describes the elements that we have in our universe, and the standard model describes the subatomic particles, the elementary particles that we have in our universe. And what it explains incredibly well, but it doesn't explain everything. So it doesn't explain where all the antimatter went.
This is a huge problem that they are trying to solve at CERN. Every particle in the universe has its own antiparticle pair. They are the same in every single way, just with an opposite charge, and if you smash them together, they annihilate, disappearing forever. But the standard model tells us that during the Big Bang, essentially equal amounts of antimatter and matter should have been created, which would then smash together and annihilate, leaving nothing behind. And yet we look around the universe and everything we see is made of regular matter. There is no antimatter planets or people walking around. But why? And to be honest, we still don't really know the answer, which is what CERN is trying to solve. And things are only going to keep getting better at CERN, because right now they are working on an upgrade for the LHC that will honestly change everything.
Right now we've collected about 10% of the data that this LHC program is designed to give us.
But what we can do and are doing is so-called high luminosity upgrades, which means you collide more protons together.
If you want to study some effects, especially in particle physics, you want to have a lot of statistics. This is what we are putting in the accelerator now. It has not been done yet. In our case, that means more collisions. And one of the ways to get more collisions in the accelerator in general is to, well, you could put more particles, but there is a limit to what you can do. Or you can squeeze them a little bit more. So if you have two beams of particles, if they're more focused, you can collide them in a more efficient, if you want to say, manner.
Giving yourself more collisions gives you more chance to discover new particles.
So by installing those new magnets into the LHC, they will squish and squeeze those packets of protons together even tighter, meaning more collisions and better data. Before I left CERN, I knew I had to ask some of these scientists about all of these conspiracy theories I see online, saying that CERN is creating black holes here on Earth or opening portals to other dimensions.
What we're doing is maybe not understandable for everyone. So we do take the time and talk to people and try to explain what we're doing and take them serious if they're afraid of us, opening a portal, destroying the world with black holes or something, which cannot happen.
I think the science is so interesting and exciting that I wish that people were sometimes more excited about that.
And to be honest, I agree. The real science is in many ways even crazier and more unbelievable than these conspiracy theories. I mean, think about it. They are literally recreating the exact conditions of the Big Bang here on Earth in a little town in Switzerland, so we can find the rarest particles in our universe. This next clip was taken right after I came up from seeing the LHC for the first time, and I think I summarized it perfectly.
I'm just blown away that people, like humans here at CERN, have been able to make something like that. And they're studying things that physicists, 50 years ago, 100 years ago, wouldn't have even dreamed is possible. So it's pretty mind-blowing.
If we showed this YouTube video to Einstein and Bohr and all of those other amazing physicists from only around 100 years ago, I'm sure they would be mind blown by the amount of progress that we have already made. And I'm sure they would also have subscribed, just like you will right now.